and get this set. Ah, hello. All right. He's telling me that my speaker is not working properly. All right. So happy Friday. My goal for us is that we will do, and I know it sounds like, whoa, whoopee, 4 problems, but we will work through 4 problems that show us pretty much every type of problem that may come our way. So that will leave us on Monday with 1 other sample problem. So I would like us to do at least 5 total problems together to learn ICE tables. So I've been very purposeful about which examples to look at. So every one of these 5 examples really shows us something different. The first one will just really expose us to the fundamentals of how we approach equilibrium problems, and that's found on page 9, and we started this yesterday. I'd like to do 4 problems today. That will leave the 5th problem for Monday, and then the last topic, which is Le Chatelier's principle. That doesn't involve problem solving, it involves interpretation of equilibrium. Then we will begin practice problem solving. We will practice on Tuesday an E day. We'll practice on Wednesday an A day, and then we'll assess ourselves on Thursday. Again, my goal for us is 4 example problems today. And if we do that, we easily can work our way through test 1.7, maybe even a little further. Le Chatelier's principle is test 1.10. Okay, so if we want to wait, on those until we see that 5th example, I would suggest working our way through these tests before we take a look, but it's absolutely your call. All right, so we are going to jump in to this problem on page 9. Any questions on what we've covered thus far before we jump in? We understand how we can interpret K, if we're given a value of K, how to make a decision about which side of the reaction is favored, what equilibrium involves, how do we get the equations for K? We are jumping in. All right. I want to make sure that it is crystal clear the expectation for our problem solving. So the way we approach an equilibrium problem, as I started yesterday, is we first write the reaction. It's up to you if you want to include phase symbols or not, but we know we want to be accountable for phase symbols because that dictates what, of course, is present in our equilibrium expression. To the right of the reaction is where we put our equilibrium expression. And then we're creating what ultimately will look like a table. And we're putting a designation for each row. And as we went over yesterday, we called it an ICE table because I is the initial concentration, C is the change, E is equilibrium, concentration. All right. That's what we got at yesterday. So first, ICE tables may only have values of molarity or pressures, period. So we can't put masses. We can't put moles. What goes into the table is values in molarity or pressures if they're gases, because we're going to use these values for K or use K to get these values. And we need concentration, or we could have Kp and then these are pressures. All right, so let's start filling in. And the reason, we set this up this way is because vertically, this is where I will place the ICE about PCl5. And then vertically is where I'll place the information about PCl3. So you don't have to draw like the table, But I'm just gonna just show you, like, what do I mean about seeing what applies to what. All right, so let's dig in. At a certain temperature, a 1 liter flask initially contained 0.298 moles of PCl3. This gets molarity. So honestly, I will share, man, when I see that we have a 1 liter flask, yippee, I'm dividing by 1. So my mole amounts directly become molarities. So I will then have 0.298 molar of PCl3. And I don't have to write MPCl3 because I'm writing it underneath this. So I know that means this species. And it's up to you if you want to keep it in scientific notation or not. We have this many moles of the PCl5 in the 1 liter flask. So yay, this divided by the 1. And even if you had to calculate what the molarity is, you don't have to show me that work. We just have to make sure, of course, that we are getting our correct values and appropriately placing them with the correct species. All right. After the system had reached equilibrium, so initially, that's what we have. Then at equilibrium, this is how many moles I have in the flask, which is still the 1 liter. So at equilibrium, here's my chlorine, I have 0.00200 molar chlorine. All right. Calculate the equilibrium concentrations of all species. So I am trying to find, E for this, and E. Oh, I already have one of the 3. That's nice. But that's my goal, but also the value of K. All right. We have some missing information. We have some missing parts of the table that ultimately will guide us in finding this. Okay. We are not told anything about starting with chlorine. It just says you have this flask and you initially have this and this. So that means we don't have any chlorine. If they haven't said, and also chlorine, we know it's 0. All right. So if this question asked us, okay, starting with this amount of this and this amount of this, how much will you get? And it was a single direction arrow previous to equilibrium, then we would know, oh, well, 1 mole of this makes 1 mole of that and 1 mole of that. And so if we have this many moles of reactant or we could calculate, we could do basic stoic. But with equilibrium, we have amounts of everything. We don't just make product. We make some product and some product can make reactant. We have back and forth flowing. We're not just pouring into one bin. That's where the change row comes in. So what makes equilibrium problems different, we don't know right off the bat how much of product we're going to be making or reactant we're going to be making initially. We're not even given a K value to let us know, oh, we're going to favor product, so we're going to make much more of that or whatever. Okay. No matter what, we will be working to get to equilibrium. So if we think about our water pouring activity, we never started at equilibrium. Wherever we were starting, which could have included some water in the product bin, we always were pouring more water from one bin into another. Each time. No matter what we're starting with, we were always transferring more water into one bin than another, no matter the size of the beakers, if we can remember back to that. So this change reflects that. What the change reflects is, okay, where are we going to be pouring more water or making more of? And we're either going to be making more product or making more reactant. From the given information, we don't start with any of this, but we end up with that. So we had to have made more product. Yeah? Well, we can't just make one of the products, we have to make both of the products. And how do we make product? We take away from reactant. Okay? Now, if we ever are missing a product, we're always going to then work to make some of it. We can't be at equilibrium without some of everything. That never will be contradictory. So you'll never have zero of product and zero of reactant. We're either, if you have zero of something, it's going to be product or it's going to be reactant. Okay, well, again, like how much? Well, we don't know yet. We just know, so if we want to call it X, we know as much of this that we make, well, because it's a 1-to-1 ratio, I'll make that much of the PCl3, and then that much of the PCl5 will have reacted away. We're reflecting the mole ratios. If this were a 2, then it would be 2x in respect to 1x. If this were a 2, it would be 1x in respect to 2x. Okay, so all we really have first is, okay, so we don't know our x yet. All we know is an expression including x to start from. So at equilibrium, the PCl5 will be this 0.00870 molar minus x. The PCl3 will be this 0.298 plus x. And then the chlorine, 0 plus x, but let's just say x. Well, the problem told us at equilibrium, that's how much chlorine we have. And so the problem is telling us our x. Now, if this were 2x, if that was a 2, and this was 2, then that value would be 2x, and we'd have to divide by 2 to get x. Okay, so if we know x, don't we just interpret it? All right. If you already have shown what x is, then you don't actually have to write 0.298 plus 0.0020 molar. You can just give me the answer. As long as you've shown, okay, that's my x. And then I'm just going to apply it. And so what we get for the PCl5 is 0.00670. And again, it's underneath the PCl5, so I know that's talking about it. And then this will be 0.300 molar. And then this, of course, is 0.00200 molar. Okay, and then we have equilibrium concentrations, but it also asks us for K. All I have to do is plug and chug. So the PCl3 and the Cl2. Nice one. They're all just to the first power. And we get 0.0896. So the teacher and me can't help but want to, like, I don't know, really make sure that the answers stand out. So what do we need to show? The reaction, the K expression, the letters ICE, this filled out, these values, the values in the K expression, and then the value of K. I'm just gonna box this in and box this in. Yes.
Would we need to show the link for I like 0.9 molar plus 0.02?
No, because if I show that this is my value of X, and then I have this E first as what would we call this? Like an expression in terms of X. If I've identified X, I can just have the answer because we know, oh, well, there's X. You just applied that to get that. So no. Okay, so next, I think laying that foundation, you guys can tackle this on your own. In a minute, I'll do this simultaneously, and then we'll check in with each other. what differs here, we are starting with a bit of everything, but we're told, just like the previous problem, about one amount at equilibrium. So if we start with 1 molar, but at equilibrium, it's higher than that, we must have added to the reactant side, okay? Well, you can't just make more of one reactant without the other. So add to both of these. How? Because this gets reacted away. And we just have to be sure that the correct coefficients identify these amounts of X. Then I come up with the expression that includes X. This plus the 3X equals that. And so that allows me to find what X is. And then applying it. And we're not asked for K, we're just asked for the concentrations. Oh, it just asked for the concentration of nitrogen and ammonia. Sorry, I also, but that's fine. Okay, question. Oh, by Monday, we'll be able to do this in 30 seconds. So quick. We considered these issues yesterday. So equilibrium position, what bin has more water, what side is more favored, and equilibrium constant, that's your capital K. All right, so now, in the AP daily videos, whenever the equilibrium expression was first communicated to you, the teacher did not call it K, she called it Q. K is only and always at equilibrium. Q is if you're not sure if you're at equilibrium. So I know a fellow AP teacher that says to his students, if you're questioning if you're at equilibrium, if you're not positive, it's Q. And usually you're starting with the initial amounts that you're given in the problem. So we usually, it's still the law of mass action. So it's the same equation we would apply for K, but we don't think these are the amounts at equilibrium. So then we can't call it capital K. And the value of finding Q is so we can figure out, okay, in what direction do we need to pour more water? Do we need to make more product to get to equilibrium or more reactant? Okay, so the value is found here. All right, so here's our Q. Our K would be the same exact equation. It's just at equilibrium. So it would be, the concentration in this reaction of C. See, you don't have to write this, you know this. I'm just going to write it for comparison's sake. Okay, all right. And just a reminder, it's product over reactant, product over reactant, product over reactant. We know that. Okay, let's start here. So, you start your problem and you're given amounts of stuff. I do. Do you see in, yep, help yourself, sir. Oh my gosh, I will keep you any time of any day. That sounds really creepy. Are you good to be here? Your teacher knows where you, oh my gosh. Open invitation, any of you guys, and I know that's like super creepy, but totally honest. Where else would you want to hang out? Hey, Stephen, oh my gosh, no question, no question, no question. All right, you're not sure if you're at equilibrium. Well, this tells us if we are. So if Q is equal to K, I know I didn't need to write that again, but if Q is equal to K, then you are at equilibrium. We don't need to pour more water in one of the bins. We're good just the way we are. But that pretty much is not what's gonna happen. Q is either going to be greater than K or less than K. All right, so what does that mean? That helps us to decide which side are we adding and which side are we subtracting from. For Q to be greater than K, okay, it is product over reactant, product over reactant. If this is larger than what it should be at equilibrium, we could either say, Aiden, because compared to equilibrium,
Either the concentration of the reactant that they're output
so we're trying to say, like, where are we? Where are we? So if we're given these initial concentrations, that's what we have in our vessel. So to get to equilibrium, so you're talking about like that's going to go. So how do we know like what's going to increase or decrease? Well, if this is bigger than this, we could say we have too much product or we don't have enough reactant. We have too little reactant. We are getting a larger number because this number is too big compared to what it would be at equilibrium. And this number is too small. And we could look at it either way. And so what you said, Aiden, so what direction will we move to get to equilibrium?
It's shifting towards
Yeah. So there's several different ways that we can say this. The reaction will shift left. We could also say the reaction will favor reactants. We could say that the forward rate will increase. Yes, sir. Oh my gosh, the reverse rate. I'm so sorry. Thank you. Oh, or we could say the reverse reaction is favored. So, oh my gosh, there's so many different ways. And you just choose what like just appeals best to you. So what's going to happen here? Okay, if we're favoring reactant, so we're starting like at this like balance, but what's going to happen is this arrow is going to become much bigger. So we need to make more reactant. So that's what we're going to do to then get to equilibrium. Then if Q is less than K, we need to make more product. So we would say the reaction then shifts right. Or the reaction will favor product. Or we should say really favor formation of product or production of product, sorry. Because if I just say favor product, it sounds like, you know, an equilibrium position. The forward rate, there we go. The forward rate increases as compared to the reverse rate. Okay, and if you sit down and just wrestle with that and really make it your own so that you just move with it. So we should get so comfortable that we really don't have to think, okay, Q is less than, and so wait, what does that mean? Which way do I move? All right, and we will get there through practice. We know that. So let's look at page 12. And tackle this with what we just learned. Carbon monoxide reacts, Sophia. Steam. What is that? Yeah. Why didn't they just say water? Water, we would definitely assume means liquid, unless otherwise told. So steam is definitely telling us gas, which then means it's going to influence the equilibrium constant to produce carbon dioxide, which we know is a gas, and hydrogen, which we know is a gas. Ryan, is our reaction balanced? Yeah, we're good. All right, now I'm just going to do this now because I know this is expected of me, and that is the K expression. Good golly, I should have left myself more room. Of course, I mean, if you didn't leave yourself enough room, there's nothing saying you couldn't write it below or something else like that. But I want to show best practice. Oh, again, man, just makes it a little easier when everything is to the first power. The equilibrium constant is 5.10. So I know I am slightly favoring product. Might as well go ahead and do my ice table. Okay, calculate the equilibrium concentration of all species if 1 mole of everything is added to the 1 liter flask. Huh? Thank you for such nice, easy math. 1 mole divided by 1 liter. You don't show that work, of course. So that means we are starting out with 1 molar of each reactant and 1 molar of each product. And we are trying to find the equilibrium concentration. Very different. The first example, we had 0 of a species. We have some of everything. And they both, 2 examples, gave us amounts at equilibrium. So what do we do? Aiden.
So for each one of the products needs to be 5.1 times greater than each one of the reactants.
I love that.
Because I don't know how to I don't know how to explain it, but you could, I wonder if you could divide, because they're starting at the same initial concentration, what if you could divide A by 2 and have that be 10?
Why divide by 2? Because there's 2 why divide by 2?
Because the products will go up by the same amount that the reactants.
Okay. Okay, but I think there may be a more direct way, especially we are really blessed with this example because 1 to 1 to 1 to 1 mole ratio. How rare is that? And 1, 1, 1, 1. How rare is that? So we could definitely go the route you're thinking, but can I just show us that every time we'll deliver? Rachel, did you have a thought?
No.
I bet you did. If we are questioning where we are, we find what do we just talked about it. That's all right. All right. We know as chemists that Q is the same equation as K. So we do not have to rewrite that. We just plug and chug. All right. Stephen, I know that you're not thinking of this, but I think maybe the average AP Chem student, you guys are not that, might be thinking, Gerhardt, are you kidding? You actually are going to write 1 molar, even with all those zeros, times 1, divide by 1, divide. Yeah. Again, how fortunate were we that we got these numbers? All set? Oh, bless you. Thank you, sir. You as well. Enjoy your weekend. Okay. Well, now what? Well, now we interpret this. Q is less than K. So the reaction will shift left to right. Got to wrestle with this until no thought is needed. You just know you're going to shift right. We need to make more products. So what does that mean? We are adding and subtracting. And it is 1x, 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 1x. So this will be 1 molar minus x, 1 molar minus x, and these will be plus x. All right, we got to find x. Well, we know the value of k. So I already have my equation. I'm just going to plug in my values. And you know what? I see that these are both the same expressions. So I'm just going to square them. Same with these. We can take the square root of both sides. This will be 2.26 equals 1 plus x over 1 minus x. I'd multiply both sides by the 1 minus x, distribute, and then we find our x value, which here is 0.387. Then we employ them to find out that our concentration of carbon monoxide is 0.613. Same for water. The carbon dioxide would be 1.387 and your hydrogen 1.387. Okay, glorious students. Oh, sugar, I was hoping for 4 examples, but we got 3 under our belt. All right, we still are great with our pacing. Concerns as you pack up. All right, have a really, really good rest of your weekend.